So, hi Swati, since you are the only one here right now, maybe let's just wait maybe 5 or 10 minutes so that a few others can join if anyone else is joining. So we'll get started in like let's say 10 minutes. Till then, I'll just mute myself. Okay, so I guess no one else is joining in person. So, hello Swati, and hello to everyone who's watching on YouTube. So, just to introduce myself, since I guess this is the first time we are meeting, so I'm Lakshya Saggi. I'm the problem solving TA for the NPTEL Selected Topics in Algorithms course, and I believe this will be our first problem solving session. We were supposed to have problem solving sessions for the previous 2 weeks also, but I was uh, I was traveling at the time, so I was not able to take the session. So sorry for that. So this will be the first session, and in this session we'll be talking about the week three contents because now we are in the third week of the course, which is essentially about randomized algorithms. So we'll be discussing a bit of problems related to randomized algorithms. So, yeah. So, Swati, at any point of time, if my audio is not clear or my screen is not visible, please feel free to inform me via chat. I'll try to address the issue as soon as possible. And if there are, like, of course, if there are any doubts at any point, like, feel free to ask them also. And I'll try to, like, clear those doubts. So, without further ado, maybe I'll just share my screen then. So, let me just share my screen. Mm. Okay, so I hope my screen is visible. Maybe we'll just say it as week three. Yeah. Uh, okay. Let me just. Okay. So I hope my screen is visible, Swati. If it is not, please inform me. Okay, it's visible. That's nice. So maybe we just get started. Yeah. Um, okay, never mind. So yeah. So the plan for today will be first, we'll maybe just discuss what was discussed in this week's lectures on a very high level. Of course, this is not a substitute for lectures, but sort of a quick revision so that everyone can understand what all main topics were discussed this week. And after maybe a quick revision, I have some problems prepared, and we'll try to. And these problems might be helpful in your further understanding of this week's content. So we'll be discussing these problems after the revision gets over. So maybe let's just straight up get to revision. So and of course, like as I already told, like feel free to ask any questions at any point of time in the chat. So this week we started discussing about randomized algorithms and some of the algorithms you may already know, like you might know quicksort is randomized, and similarly Kargar's min-cut algorithm was already discussed in the previous weeks. So that also is a randomized algorithm. What is a randomized algorithm? Essentially, an algorithm which uses randomization. So the algorithm is not deterministic. So usually there is a bifurcation for the kind of randomized algorithm. So usually we say that there are two kinds of randomized algorithms. One is the Las Vegas kinds of randomized algorithms, and other are Monte Carlo randomized algorithms. So the characteristic for Las Vegas algorithms is that they always so essentially an algorithm has two kinds of characteristics. An algorithm should be correct, and also it should be efficient. So it should have a good runtime, as well as it should output the correct output. Like its output should be correct. So the Las Vegas kind of randomized algorithms usually have the correct output, but their runtime is random. So we can talk about expected runtime for these Las Vegas algorithms, but their output will always be correct. And quicksort is one example of that kind of algorithm. Whereas the Monte Carlo randomized algorithms may have wrong output sometimes, but their runtime is not random. Their runtime is fixed. For example, the Kargas min-cut algorithm always has a fixed runtime, but it may output the wrong min-cut sometimes. So Usually, out of these Las Vegas and Monte Carlo randomized algorithms, generally we prefer these Monte Carlo randomized algorithms. Generally, they are preferred because their runtime is runtime is bounded, so the runtime is not random, and this thing of having wrong output sometimes can be fixed by running the algorithm multiple times. But if the runtime itself is random, then it's sometimes becomes a bit of an issue. So although both kinds of algorithms are we can discuss both sorts of algorithms, but usually like Monte Carlo randomized algorithms are much more preferred. If we can obtain a Monte Carlo algorithm for a problem, it's much better than obtaining a Las Vegas randomized algorithm. So yeah, but other than that, for the first problem which we discussed in the context of randomized algorithms was this polynomial identity testing problem. And what's this polynomial identity testing problem? So suppose you're given two polynomials f and g, then what we have to compute is whether f and g are polynomials which are equivalent to each other. So, so note that uh, if these polynomials are given in this form, like if the f is given in form of like if these polynomials are like functions of x1 to xm, and we are explicitly given like the coefficients of these polynomials for like different the coefficients of the different monomials in these polynomials, then we can just straight up compare all of these coefficients, and then we can say whether these polynomials are equal to each other or not. But usually these polynomials are not given as these explicit polynomials, but instead they are given as some oracles or something. So what you can do is you can evaluate these polynomials f and g at some point of your choice, and then you have to answer whether these polynomials are equal or not equal. So then this polynomial identity testing problem, like uh, this is kind of the main issue, that you're not given the polynomials explicitly. Otherwise, you just check these coefficients whether a is equal to b and things like this. But usually the polynomials are not given explicitly, but they are given in implicit form, whether in which you just have you can give a like some points as input, and yeah, suppose you can give some point as input, let's say point alpha, and then the oracle will tell you what's the value of f of alpha, and similarly what's the value of g of alpha, and then you have to answer whether these polynomials are equal or not. And this problem of saying whether f equal to g is equivalent to saying whether f minus g is equal to 0. So polynomial identity testing is equivalent to asking whether it's equivalent to saying polynomial zero testing, whether this certain polynomial f minus g is 0 or not. And usually, how do we go about it? So, so there exists a very nice randomized idea for this, which is based on this Schwarz-Zippel lemma. So, on a very high level, what suppose if you have to compare whether f and g are equal or not. So, how do you do this? So, it can happen like suppose you give some point alpha. Like suppose you evaluate these polynomials f and g at some point alpha. So, it might happen that f of alpha might be equal to g of alpha. But it does not mean that f and g are equal to each other. It might be that f and g are equal on this specific point alpha, but might not be equal in general. So this kind of creates a bit of an issue, and that's where randomized algorithms come into the picture. So essentially, to test whether f is equal to g, let's just say we just check at a random, uniformly random point alpha. So we do not fix the point alpha beforehand at which we will be testing whether f is equal to g. So we'll just evaluate f at some random point alpha, and we'll evaluate g at that same random point alpha. And then if that at that random point, if f of alpha agrees with g of alpha, then we can say that okay, even if at a random point these polynomials agree, then it's very likely that these polynomials are equal to each other. And this is kind of captured very nicely mathematically by the Schwarz-Zippel lemma. So Schwarz-Zippel lemma essentially says that uh, suppose there is a polynomial in n variables, the polynomial p is a non-zero polynomial in n variables, and the total degree of that polynomial is d, where the total degree has was also defined in the lectures. It's just the maximum degree over all the monomials, and a monomial can have a lot of variables in it, and so the degree of the monomial will be just the sum of the degrees of all the variables inside the monomial. So yeah. Just a reminder, what is the total degree of a polynomial? So essentially, what Schwarzschild lemma says is that let P be a non-zero polynomial in n variables of total degree d over a given field f. So we'll assume that, yeah. And like let's say the subset S be a finite set, then if x1 to xn are drawn uniformly at random from S, from this finite subset S, then the probability that the polynomial, when evaluated at this uniformly random point x1 till xn, will be 0 is less than equal to d divided by the size of S. So essentially, on a very high level, what's this lemma saying is that this x1 till xn is a random point from this finite set S. So if you evaluate at a uniformly random point uh, from a subset S, then the probability that the polynomial will actually be equal to the polynomial evaluation will be actually equal to 0 is very low. It's bounded by d by size of S, given that the original polynomial is a non-zero polynomial. If the original polynomial is, of course, a zero polynomial, then at every point its value would be 0. But if the original polynomial is a non-zero polynomial, then if it is evaluated at a random point, then the probability that the evaluation gives an answer of 0 is very low. Like it's d divided by size of S. And the size of S you can make like very large, like let's say d cube, d square, or anything you want. So this is what Schwarzschild lemma says. So essentially, what this kind of gives us is that okay, if you are given a polynomial in, let's say, this oracle setting where you're not given the polynomial explicitly, but you're given it implicitly, then how do you uh, compute whether that polynomial is 0 or it is non-zero? So just test it at a random point and check whether the value comes out to be 0 or not. And with very high probability, if the value comes out to be 0, then the polynomial will actually be 0. So I hope this makes sense. Yeah. So now, so this is what Schwarzschild lemma captures. So essentially, like this is a very useful tool, usually used in these kinds of randomized algorithms or in general algebraic algorithms, because you can express anything, if you can express any quantity in form of a polynomial, and then you need to check whether that polynomial is zero or non-zero. Then you just plug in random values for the variables, and then if the polynomial turns out to be 0, then the actual polynomial you can say is also 0. So yeah. So this Schwarzschild lemma is one of the most useful tools actually in algorithms domain. So yeah. So coming to some of the applications. So polynomial identity testing is one of the applications, but there are some other more algorithmic applications of this also. For example, detecting whether there exists a perfect bipartite matching. So given a bipartite graph with bipartitions U and V, the problem is we have to detect whether there exists a matching where every vertex is matched. So I hope everyone knows what is a matching. Uh, so given a bipartite graph, we have to answer whether this bipartite graph admits a perfect matching on. So one way is, of course, to express this problem as a flow problem and solve it. But in terms of these randomized algorithms domain, there exists another very elegant method, and the method is like this. So suppose we denote by matrix A the bi-adjacency matrix. Essentially, matrix A is nothing but uh, n cross n matrix where I comma jth entry is 1 if and only if ith vertex of U has an edge to jth vertex of the set capital B. So essentially, this matrix A captures the adjacency of the graph G. Uh, okay, so I just saw that Mridula has also joined the chat. So Mridula, just to uh, uh, just to maybe capture on a very high level what we are discussing. So yeah, we are discussing this week three's, just as a recap, we are discussing this week three's content, which is about randomized algorithms. So right now we are just kind of revising or recapping on a very high level uh, what all was discussed in the lectures, the main things which were discussed in the lectures. Of course, this is not a substitute for lectures in themselves, but just a quick recap. So yeah, so we discussed what are randomized algorithms, what is polynomial identity testing, then what is short simple lemma, and now we are trying to see some applications of the things which we discussed. So first application which we are discussing is testing whether a graph G contains perfect bipartite matching. So suppose we have this A as a bi-adjacent. So at any point of time, if you have any doubts, Mridul or Swati, like feel free to ask in chat. Like so, yeah. Uh, so so if A is the uh, bi-adjacency matrix of the graph G, then what one can do is maybe construct another matrix A prime such that the I comma jth entry of the matrix A prime is nothing but Aij times Xij, where Xij is some kind of a variable. So Xij is some variable. So essentially, what we are doing is so this matrix A prime, what this encapsulates is that so this note that this Aij entry is one if and only if there is an H between I and J, and otherwise it is zero. So A prime I comma the I comma jth entry of this matrix A prime is zero if there is no H from I to J, and it is equal to Xij if there is some H between I and J in the graph G. So A prime matrix actually is a kind of a polynomial matrix because all of its entries are like some kinds of monomials. So the I comma jth entry of A prime is Xij if there is an H from I to J, and otherwise it is zero. And now what one can do is um, let's just say we define this polynomial P of Xij as the polynomial which is like determinant of this matrix A prime. So the determinant of this matrix A prime uh, is this polynomial P. Let's say we call this polynomial P as the determinant of this matrix A prime. And then it was shown in lectures that this polynomial P is zero if and only if G has no perfect bipartite matching. So the determinant of A prime is actually a zero polynomial if and only if G has no perfect bipartite matching. So if G admits perfect bipartite matching, then this polynomial will actually be non-zero. And then how do we test whether the graph G actually so we cannot compute this determinant in terms of these polynomials because it will be very expensive because there will be n factorial kind of terms. But what one can do instead is maybe just so this is just try we are just trying to find out whether this polynomial is zero or non-zero. And we know that using Schwarz-Zipper lemma, how can this be done? Just substitute uh, uniformly at random value, like just substitute values from a uniformly random distribution to all these xij's. So just substitute uniformly random values for all of these xij's and evaluate this determinant of the matrix A prime for those substitutions. And then if the determinant comes out to be zero, then actually the graph has no bipartite matching. Otherwise, the graph G has a perfect matching. So yeah. And the main idea on which this argument hinges on is that the polynomial P is actually the determinant of A prime. And if you write out the determinant of this matrix A prime, so each monomial in this determinant, so this determinant will be a polynomial in these Xij variables. And yeah, and each monomial actually captures each of the perfect matchings in the graph. So actually, each of the monomials in this determinant will capture each of the perfect matching which is in the graph. So if there is no perfect matching, then there will be no such monomial, and then this polynomial P will be actually equal to zero. So yeah. Okay, so this was an exam, and computing determinant of matrix is kind of there's a lot of research work which already has been done into it. It can be done in like end to in matrix multiplication time and so on. So there are like very nice algorithms to test to find out the determinant of matrices. So yeah. So moving on after this polynomial identity testing, there was this discussion about randomized quicksort. So what is randomized quicksort? Maybe just select uh, some pivot x at uniformly at random from the matrix A, and then just partition the array A according to this pivot x, and then we'll obtain these two arrays A1 and A2, and then just recursively apply quicksort on these subarrays A1 and A2. And then it was shown in the lectures that expected number of comparisons in this randomized quicksort is n log n. Note that in worst case, the time complexity can be order n square. If you're always choosing this pivot as some very bad quantity, like uh, like suppose this pivot x always tends to be the greatest element of the array. Suppose initially you choose this pivot x as the greatest element of the array. Then what's going to happen is this array A1, which is the smaller subarray, the subarray to the left of x after partitioning will have size n minus 1, and this A2 subarray will be of size 0. And then recursively applying, suppose on this A1, if you again choose the greatest element of this A1 as the pivot, again the remaining subarray will be of size n minus 2, and then n minus 3, and so on. So the time you will spend is about n order n plus n minus 1 plus n minus 2, which will be approximately order n square in the worst case. So the key idea in this randomized quicksort is you are not selecting actually like, so if you select always uniformly at random, so if you don't select this like, so if you select this pivot x uh, as a uniformly random element of the array, you don't select this pivot x as, let's say, some deterministic value like the maximum or the minimum, but rather something uniformly at random from the array. Then actually you can show that in expectation, the total number of comparisons you need won't be order n square, but rather will be order n log n. So this is one example where power of randomization is pretty evident. That if you selected deterministically this pivot, let's say you selected deterministically the greatest or smallest value or anything, then you can always have very bad run times for quicksort or n square run times. But if you just say that you'll always pick this element uniformly at random, then the number of comparisons goes down to n log n. And the key lemma which was used to show this, uh, which I feel is one of the most beautiful arguments out there, uh, like in an introductory course to randomized algorithms, is this argument that so consider any pair of elements I and j. So we are trying to find out. So the expected number of comparisons we need to show is n log n. So essentially, we need to show that for any pair I and j, whether I and j are compared or not, and we need to bound like how many pairs are compared in the execution of this randomized quicksort. So suppose we have this final sorted array C, and in that final sorted array C, let the ith element and jth element be like any two elements. Then we say we assign a random variable xij, whose this is an indicator variable whose value is 1 if Ci and Cj are compared during the run of this randomized quicksort algorithm, and otherwise it is 0. So essentially, what we are trying to do is we are trying to check for all pairs I and j whether I and j were compared at any point during the run of the algorithm. I note that even if they are compared, they can only be compared at most once. We don't ever compare any pair twice. So what we do is for any pair I and j, this value is 1. So this contributes one comparison if Ci and Cj are compared at any point during the execution of the randomized quicksort, and otherwise it is 0. And so what's the expected value of xij, this random variable xij? It will be just equal to 1 times the probability that Ci and Cj are compared at any point, plus 0 times other thing. And 0 times any other thing will cancel out to be 0. So this is just equal to probability that Ci and Cj are compared during the execution of randomized quicksort. And what will this be equal to? The probability that Ci and Cj are compared. So this will be equal to, so note that at any point during the run of this randomized quicksort, suppose the pivot selected was one of the elements to the left of I. Then that pivot won't separate I and J. So still in one of the subarrays, I and J both will be present. Similarly, if the pivot was present on right of J, still like I and J won't be separated. So when will I and J be separated actually? When the pivot is chosen from one of this subarray, the subarray which starts from I and ends at J. When the pivot is chosen as one of the elements from this subarray, then actually I and J will be separated and they won't be ever compared again in the algorithm. And so note that, and from this subarray from I to J, there are like J minus I plus 1 elements in this subarray. And out of these, when will I and J be compared? When the pivot is chosen to be either I or J. So there are two possibilities when I and J will be compared. When the pivot is either I or J, so the probability in the probability the numerator is 2, and the denominator is the total number of possibilities of the pivots, which is this the size of this subarray, which is like J minus I plus 1. So out of these J minus I plus 1 pivots, if either I or J is chosen as the pivot, only then will they be compared. Otherwise, what's going to happen is if you have any other element as the pivot, then I and J won't be compared directly, but they'll be compared to this element, let's say this selected element pivot, and then I will go to another other subarray and J will go to another subarray, and then they won't be ever compared in the future in the algorithm. So that's why there are like two ways in which they can be compared, divided by J minus I plus 1. So essentially the expectation of this random variable that that I and J are compared, the expectation of this random variable is just 2 divided by J minus I plus 1. And summing this, and what we need to do is we need to find out the total number of expected number of comparisons in the algorithm. So you will just sum it over all possible I and J's. And this can be, so the sum over all possible I and J's for this thing can be shown to be uh, n log n. And that's how we get the result that uh, quicksort has order n log n expected runtime. So note that I'm going over the details in a kind of a faster manner because uh, I'm assuming that you guys have gone through the lectures and yeah, this is more of a recap rather than a substitute for the lectures. So, so yeah, so we from this we get the theorem that for every input, the expected number of comparisons by randomized quicksort algorithm is just order n log n. And one important thing to note actually in the case of randomized algorithms is, so the expected number of comparisons is for any input. So this should not be, so sometimes people get confused between average number of comparisons and expected number of comparisons. So this thing should not confuse you actually. So this is a kind of a very important thing which a lot of people sometimes uh, 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 get wrong. That sometimes people think that okay, like what this means is that on any input, the average cost of the quicksort is order n log n. But this is not what this means. So what the statement means is that suppose you're given any input and you run quicksort on that input, then it will take like order n log n time in expectation to sort that input array. Whereas what this average cost means is that so input is picked from a distribution. So what this average cost means is that suppose you are picking, so what you can do is, so there are two kinds of randomizations. What you can do is you can have some input fixed and then run this randomized quicksort. Another thing can be you can have the input also as a distribution and then find out the average cost uh, of sorting that input distribution. And that's what gives you the average cost. I note that. So that's why like these kinds of things are like very separate quantities. Here in the notion of reflected cost, the input is fixed, whereas in the notion of average cost, the input also comes from a distribution. So what we have just proved is this expected cost. So this is a much stronger notion that for any input, your algorithm will take an expectation at most n log n time. Whereas what average cost notion says is that there will be some inputs on which the algorithm can take very larger time, and on some inputs it will take lesser time, and averaging over all the inputs will actually give like some like n log n time. Whereas expected cost says that on every input you'll actually get n log n time. So yeah. So this is kind of a important uh, difference, and I think that this should be appreciated that we are talking about expected costs here, not average cost. And after that, so after discussion of this quick sort, there was discussion about these concentration bounds. So I won't go into the proofs of these, but these concentration inequalities are kind of really important for us. So we should be discussing these. So Markov inequality says that so one of the most basic concentration inequalities, but very useful, is this Markov inequality, which says that if x is a non-negative random variable and c is any positive real number, then probability that x is greater than equal to c will be less than equal to expectation of x divided by c. And it does not have it. Proof is also simple. Proof is not quite complicated. And this might seem like a simple statement, but leads to some very interesting bounds. For example, there is a Chebyshev inequality, which can be derived from Markov's inequality. So essentially, which says that if x is a random variable with a finite expectation and variance sigma star, so expectation mu and variance sigma square, then for any positive real number c, probability that x minus mu is greater than equal to c will be less than equal to sigma square divided by c square. And yeah, and after this, there is another inequality which is like concentration inequality, which can also be derived from like Chebyshev and Markov inequality, but this is a much stronger statement and very useful, like which are Chernoff bounds. These are used a lot in like theoretical computer science. So Chernoff bounds are one of the most important tools in algorithms, in randomized algorithms per se. So what Chernoff bound says is that suppose x1 to xn are n independent random variables which take the value either 0 or 1. And let's say there's a random variable s, which is the sum of these n random variables. And if expectation of s is equal to mu, then what we have is that probability of s greater than equal to 1 plus delta times mu is less than equal to some quantity, and probability of this is less than equal to some quantity. So rather than passing through all of this mathematics, I'll just give you a high level intuition of what's going on here. So what is essentially saying is that so let's just look at this first term. So it's saying that probability that s is greater than equal to 1 plus delta times mu. So it's saying that okay, like if if you put delta as 0, then you're just asking about whether probability s is greater than equal to mu. Similarly, if you put delta as 0.5, you're saying that probability s is greater than equal to 1.5 times mu. So the Chernoff bounds are actually stating whether what's the probability with which this random variable s deviates from the mean mu. So in a distribution, we know that we know that the mean of s is mu. So the with what probability does this random variable deviate from its mean? This is what the Chernoff bound is talking about. And there is a less than equal to sign. So it's essentially bounding the probability by which a random variable can deviate from its mean. So essentially, Chernoff bound is saying that uh, so if we are given these parameters, then the random variable s uh, cannot deviate from its mean by a very large quantity. Like the probability with which the random variable s deviates from its mean is bounded by it has some kind of an upper bound. So it cannot be that it deviates very away from its mean. It is for the random variable s uh, will have bounded deviation from its mean. So this is essentially what Chernoff bound is saying on a very high level. And there are so this is how you should pass the statement that Chernoff bounds or any of these concentration bounds try to bound like how much is the random variable with what probability is the random variable going away from its mean. and then these bounds prove some kind of like these concentration inequalities prove some kind of probability bounds that okay it goes away from its mean with at most this much probability or something like this. And similarly, this thing also. So the lower bound also states that so it goes like it says that it goes away from its mean on the positive sign with some bound probability. Here it says that s is less than equal to 1 minus delta times mu, which means that s goes below mu with some bounded probability. So most of the probability mass of S is centered around its mean only, and the masses on the extremes are kind of low. This is what essentially Chernoff bounds are saying, if it makes sense. So yeah, and there are some further much more usable. So this kind of formula is complicated, but there are some more usable forms of Chernoff bounds which can be derived from this formula only. So so this multiplicative form is I think the most used form in the algorithms domain because usually you want to look at the probability bound when you're not going a lot away from. So if you just have delta between 0 to 1, you can have some much more cleaner bounds than this original bound. So yeah, and then there are further forms of Chernoff bounds if you want to see what happens when the deviation is very, very large. So yeah. Okay, but let's not get into that. But I think these kinds of these multiplicative bounds are this multiplicative form is I think the most used form. This is the form which like it's fine if you guys don't if you don't remember these bounds or like let's say the bounds below, but I believe that anyone working in randomized algorithms should know these bounds by heart. The Chernoff bounds for this domain when delta is from 0 to 1. So yeah. Okay then. So, Swati, are there any like doubts in the recap or anything? Like, do you want me to explain some concept again, or any other concept which I missed, which I should try to explain, or should I move on to questions? Because I don't have a lot of questions, I just have 4 or 5 questions, and they are a bit more theoretical questions. So, oh, okay, how to calculate degree? Okay, so that's nice thing. So I skipped that part. Like, I kind of went over that part quite quickly. So maybe I'll just explain it again. So what's essentially it's saying is that Swati, so what do we mean by total degree of a polynomial? So note that what's a polynomial? So let me just write it down also. So let's say I'm talking about a polynomial in let's say 3 variables. So polynomial in let's say 3 variables x1, x2, x3, and let's say the polynomial I'm talking about is something like this. So 2x1 squared x2 to the power 5 and then maybe like let's say yeah x1 to the cube x3 to the power 5 yeah plus 1. Maybe let's say this is the polynomial. So so let's say this is so what are monomials in a polynomial? So this is the polynomial in x1, x2, and x3. And what are the monomials of this polynomial? So monomials are the terms which are separated by this summation sign. So this 2x1 square x2 to the power 5 is one monomial of this polynomial. Then this x1 cube x3 to the 5 is the other monomial, and this plus 1 is the other monomial. Right. And now, what's the total degree of this polynomial? So the total degree is of the polynomial is said to be the maximum degree over all the monomials. So highest total degree of its monomials. So this is one monomial, this is another monomial, and this is another monomial. And how do we calculate degree of a monomial? So degree of a monomial is just uh, the sum of the powers. So this polynomial is a polynomial x1, x2, and x3. So we consider a monomial and just take the sum of the powers of all of these variables. So x1 has the power x1 squared. So the power of in this monomial the contribution of x1 to the degree is 2. The contribution of x2 to the degree is 5. So the degree of this monomial is 5 plus 2, 7. Because it's x1 to the power 2, x2 to the power 5. So 5 plus 2 is 7. Similarly here, the degree of x1 is 3 and degree of x3 is 5. So degree of this monomial is 5 plus 3. So this 5 plus this 3, which is 8. And this one can just be written as like x1 to the power 0, x to the power 0, x to the power 0. So the degree of this is just 0. So this is 0 degree, this is 8 degree, and this is 7 degree. So what's the maximum of 7, 8, and 1? It's 8. So this 8. So this contributes 8, and so 8 is the degree of this polynomial. So does this make sense, Swati? Yeah. So this is multivariate. Even in the univariate case, this remains the same. So for example, suppose you just have p of x is okay x cube plus x to the power 5 plus x to the power 7 plus 1. So again, this can be thought of as multivariate or univariate, anything like that. Like so multivariate is a generalization of univariate anyways. So what according to you should be the degree of this polynomial, Swati? So so these are the monomials. So this is one. So the monomials are the terms which are separated by the addition sign. So this is one monomial. This is another monomial. This is another monomial, and this is the another monomial. So there are four monomials in this polynomial. So what's the degree of this monomial? The power of x is 3. So here the degree is 3 for this monomial. The degree for this monomial is 5. For this is 7, and for this is 0 because this is x to the power 0. So then what's the degree of this total polynomial? Uh, Swati, would you like to answer in chat? Okay, Swati is typing. Okay, so yeah, okay, no worries, you're welcome, Swati. But I was just asking, like, so what according to you should be the degree of this polynomial, like, so this if p of x is this, so 7. Oh yeah, so yeah, correct, Swati. Because this monomial is 3, this is 5, this is 7, this is 0, so the maximum is 7. So good job, Swati. Yeah. Okay, maybe just another exercise, just a food for thought. So what's the degree of this uh, then x to the power 5 plus x to the power 7? Okay, maybe x to the power 3 minus 2x to the power 5 plus. So what will be the degree of this polynomial according to you, Swati? So it's not like I am grading you or testing you, it's just for a sanity check or for better understanding. Oh, so Swati is saying that the degree for this should be 5. Really, Swati? Uh, just think about it a bit. So note that this x to the 5 minus this 2x to the power 5 plus x to the power 5. So these things can be simplified further, right? So this will actually cancel out to 0. So this polynomial will actually be equal to just x cube. Does this make sense, Swati, what I'm trying to say? Yeah. So actually, like, yeah, so maybe I was a bit unclear from my end also. So degree, so the monomials are not the term, like it's not just the terms which are separated by this plus signs, but rather you have to say you have to simplify the polynomial as much as you can first. Like you have to simplify these, like all the terms which can be added or subtracted, you first add or subtract them together. And after that, so here we see that x cube, x5, x7, and 1 are incomparable. So they cannot be simplified further. But here actually there are like multiple x to the power 5 terms. So actually they can be compared with each other, and they can, like, this can be simplified further. So this minus 2x to the power 5 plus x to the power 5 plus x to the power 5 will actually give us a total of 0. So this polynomial will actually be just equal to x cube. Yeah, so 3 should be the answer. Exactly. So very good job, Swati. Exactly. So this is my point that first, so how do you calculate degree? So first you maybe simplify the polynomial as much as you can using these pluses and minuses. You simplify the polynomial as much as you can, and then all the terms which are separated by these pluses and minuses are the monomials, and then you see the maximum degree overall the monomials. Yeah. So I hope it's clear now, Swati. So yeah, uh, good job, Swati. So degree of this polynomial is 3. So, Swati, are you typing something in the chat, or it should be? Okay, Markov inequality is not clear. So, okay, so maybe I'll try to explain the Markov inequality again. So, yeah. So Swati, are you familiar with random variables? So, maybe before moving on to this concentration inequalities, what's important is we should first be familiar with what are random variables, because in the concept of randomization, these random variables are something uh, which are really important. Oh, so you are familiar with random variables, so that's nice. So, so what this Markov inequality is saying is that, so if x is a non-negative random variable, so essentially what it says is that, so suppose x is a random variable which does not ever take the value, which does not ever take negative values. So x takes maybe value 0 with some probability, 0.1 with some probability, 0.2 with some probability, and so on. But doesn't. But the probability that x is less than 0 is always 0. So if x is a non-negative random variable, and if c is any positive real number, so you can choose, c is of your choice. So you can ask, say c is 10, c is 20, or anything. Then what you can actually say is that it's always going to be the case that probability that x is greater than equal to c will be less than equal to expectation of x divided by this constant c. So essentially what it's saying is that uh, if x is a non-negative random variable, then you can choose any number c, and the probability with which your random variable will be greater than equal to this number c will always be bounded by this quantity. So your random variable cannot become very, very large. Like, so the probability with which your random variable becomes greater than equal to c will be bounded by this quantity. So so can you clarify, like, what okay, so is it clear, Swati? Maybe I also have a question prepared on this, so it might be like uh, it might make more sense after we do the question, but on a high level, does this make sense? What is Markov inequality saying? Okay, it makes sense. That's nice. Okay. So are there any other doubts? Or maybe we can first just maybe I have a question prepared on Markov inequality. Let's just first attempt that question. So maybe like it becomes more clear about Markov inequality. So yeah. So let's say so yeah, the first question is so okay, like let x be a positive random variable and probability of x. Okay, maybe not positive but non-negative. And probability that x is greater than equal to 10 is given to us to be greater than equal to 0.1. So suppose we are given that x is a non-negative random variable and probability that x is greater than equal to 1 is actually point. So probability with which x is greater than equal to 10 is uh, at least zero point 0.1. So then what is the minimum possible value of expectation of x? This is what we need to answer. Like so out of all possible random variables x which satisfies this kind of a property, tell us the x which has the minimum possible value of expectation of x. And also we need to provide an example distribution of x on which this minimum is achieved. So maybe I'll just do this so let's say so that the things become more clear. So so we know by Markov's let's just paste the Markov's inequality here again. So we know this is the Markov's inequality. So suppose we take so here we have that probability x is greater than equal to 10 term. And here we had x is greater than equal to c. So here we have put c actually equal to 10 in the Markov inequality. So taking c equals to 10. So note that x is non-negative random variable. It is given to us here also. So that's why we can apply Markov's inequality. If if x was not given to be non-negative, then we could not apply Markov's inequality. So maybe let's just write that down. Since x is a non-negative random variable, we can apply Markov's inequality. And then taking c equal to 10 in Markov's inequality, what we get? So we get that probability. So in this formula, if we say that c is equal to 10, then we get that probability that x is greater than equal to 10 will be actually less than equal to expectation of x divided by 10. So something like this. So because c I have put as 10, so this is going to be the case. But also we are given that this probability that x is greater than equal to 10, this is actually at least 0.1. So this quantity is actually at least 0.1. So this is greater than equal to zero point 0.1 and also this is less than equal to expectation of x by 10. So also we are given that probability. So maybe I'll just write it the other way that 0.1 is less than equal to probability x is greater than equal to 10. So what this gives us is, so we know that 0.1 is less than equal to this term probability x is greater than equal to 10. And this term is further less than equal to expectation of x by 10. So what we get is, hence we get that uh, 0.1 is actually less than equal to this quantity probability x is greater than equal to 10. And this is further less than equal to expectation of x by 10. And what this means is that so this thing is less than equal to this thing. And this implies expectation of x by 10 is greater than equal to 0.1, which implies expectation of x is greater than equal to 1. So what's the minimum possible value of expectation of x? If expectation of x is greater than equal to 1, then the minimum possible value is just 1. Hence, the minimum possible value of expectation of x is equal to 1. Yeah. So, uh, does this make sense, Swati? Like, I discussed this question because I thought that if we just talked about Markov's inequality, then it's a good idea to maybe discuss a question uh, just at that point only. So, is it clear, Swati? So, this is something which we were given, and we are also given x is a non-negative random variable. So, we could apply Markov's inequality, and yeah, applying Markov's inequality gave us bounds on some kind of expectation, and we could relate it to this bound. So if anything is not clear at any point, like feel free to ask. So okay, but one thing now I want to point out is that our job is not done yet. Uh, so note that we want to say what is the minimum possible value of expectation of x. From here we just what we got was expectation of x is greater than equal to 1. But this does not mean that this 1 is also achieved at any point, right? We should also be showing that this value of 1, so there exists some distribution x at which this 1 is actually achieved. So we need to give some distribution of x at which this value of 1 is actually achieved. And that's why like I also added this part that provide an example distribution of x on which this minimum is actually achieved. So can you think of a distribution, Swati, at which uh, so essentially we need to give so we need to provide a random example of a random variable x such that this thing holds and expectation of x is actually equal to 1. So can you think of such a random variable, Swati? Like, would you like to answer? Try this. Like, I can mute myself for a couple of minutes and you can think about it if you want. Like, give an example of a distribution of x. So x should be non-negative random variable. Probability of x should be like probability that x is greater than or equal to 10 should be 0.1 at least, and expectation of x should be equal to 1. Uh, would you like to think about it, Swati? I'll just mute myself for maybe like let's say 3-4 minutes and you can try this out. Like it's fine even if you don't get it right or if you're even if you're confused. Just try to think about it. That's all I'm saying. Okay, so I'll just mute myself for maybe a couple of minutes. I'll just also get some water till then. So just try it on and whatever you think does. Uh, let's just work with that. Hi Swati. Uh, would you like to maybe attempt this or talk something about this? Uh, so 0 point. So actually, we need a distribution of x, Swati. So we will need to actually give so x is a random variable. So what we need to provide is so that x is like this x takes value something like, let's say, so example of a distribution is like x probability that x equal to 5 is 0.1 and x equal to 10 is 0.9 or something like this. So x is a random variable, so it will have a uh, distribution, not just a single value, if it makes sense. Because a random variable, like you need to specify that this variable takes this value with this much probability and that value with that much probability and so on. So maybe I'll try to address this. So so we know that expectation of x is greater than equal to 1. So now we want to kind of prove a lower bound that expectation, like what's the minimum possible value that this expectation can take, right? Now, high level intuition for this is okay, so to get the minimum possible value for expectation of x, we want to have more probability mass at smaller values of x, right? So we want to have and what the smallest value that this x can take, the smallest value that this x can take is 0. So we want to say that x takes the value 0 with as much probability as we can. Ideally, we would like to say that x takes probability 0, x takes value 0 with 1 probability. But we are also constrained to give at least 0.1 probability mass to the values x is greater than or equal to 10. So if we give zero point 0.1 mass to this value 10, and we take the remaining zero point 0.9 probability mass to the value 0, then let's just see what happens. So let's say consider the distribution. So so what's the distribution? Distribution on, consider the, okay, maybe following distribution on x. And what's the distribution? Distribution is something like this, that probability that x is equal to 0 is 0.9 and probability that x is equal to 10 is 0.1. Okay. So we see that because what I try to do is I've tried to assign as much probability mass as I can to the smallest value of x because I want to minimize this expectation of x. And I've also assigned and I also have to specify satisfy this constraint that x is greater than or equal to 10 is 0.1. So so this kind of constraint is satisfied at this value that x equal to 10 is zero point 0.1. So you can see that both of these constraints are actually satisfied. This constraint and the constraint that like x is a non-negative random variable. And now let's see what's the expectation of this random variable now. So now it can be seen that expectation of x is nothing but 0 times 0.9 plus 10 times 0.1. And what does this equal to? So this is 0, this value is 0, and this value is just 1. So indeed, we have an example of a distribution in which expectation of x actually comes out to be 1. And by Markov's inequality, we also know that expectation of x is greater than or equal to 1. So this is actually the minimum possible value for expectation of x. And so this indeed is achieved. So by Markov's inequality, we know that expectation of x is greater than or equal to 1. And this 1 is indeed achieved at this kind of a distribution. So yeah, so this is the example distribution. And that's why, because for showing that some value is minimum, you need to show that anything smaller is not achievable, but you also want to say that this minimum is achievable. And this is what we show by this example. So does this make sense, Swati? Swati, does this make sense? Okay, it makes sense. That's nice. Okay, so uh, yeah. So do you want me to discuss any other concept again, or should I move on to the other questions which we have, like some of the example problems which we have, or should we maybe discuss some other concept again, revise some other concept again? Because yeah, like doing questions only makes sense after we have like grasped the concepts carefully. Yeah, okay, so we can move on to the questions there. So this was the first question which I had. Okay. And now this is the second question. So this is more of a, like a problem on random variables. I really like this question, like because uh, this teaches us how to use expectations and everything quite elegantly. So the problem is something like this. So suppose you are given R distinct red balls and B distinct blue balls, and now you take these R plus B balls. So there are these R plus B balls, R red and B blue balls, and you have a like a uniformly random permutation of these balls. So you have a like you take a random permutation of these balls. So these balls are appearing in a random order, okay, or maybe random, uniformly random order, or let's say yeah, permutation or let's say order of these balls. So these balls are ordered uniformly randomly. So like yeah, one ball is at the front, other ball, another ball, so on. And now we have to answer that what is the expected number of red balls that appear before all the blue balls. So what we have to answer is so we have these R distinct red balls and B distinct blue balls. And now if we have this uniformly random permutation of these R plus B balls, then it might happen that the first ball itself is a blue ball. In that case, there are zero red balls that appear before all the blue balls. But it might be the case that there are five red balls before the first blue ball appears. And then, like in that case, there will be five red balls. And now, over all these permutations, what's the expected number of red balls that appear before all the blue balls? So, why am I discussing this kind of a question? Because, like as we saw, like in the analysis of randomized quicksort, it was also more of a question on uh, analyzing random variables rather than a randomized algorithm. This question also is kind of on the same line. So would you like to attempt this question, Swati? So I hope the question is clear first of all, right? Like if there is any doubt regarding the question, like please ask. So the question is essentially saying that you are given R red balls, B blue balls, or balls are distinct, and then you are taking a uniformly random permutation of these R plus B balls. Then in expectation, what is the number of red balls that appear before all the blue balls? Okay, so you got the question, but you're not able to solve. Okay, so maybe we'll just discuss this. So maybe let's just try so what I'll be describing are like maybe two ways to approach this problem. So one way first we'll see, and it will be a more inefficient way. So like why am I giving this question this question is to like make you appreciate the rule of like linearity of expectation. So what's the approach one? Find the distribution. So okay, so uh, consider the random variable x as the number of red balls that appear before all the blue balls. Yeah. And then the problem essentially asks us to compute the value of expectation of x, right? So this is the problem essentially, that we are given a random variable x, which is the number of red balls that appear before all the blue balls, and then we need to find out the value of expectation of x, where expectation is taken over all these uniformly random permutations, right? So one approach might be to find actually the distribution of the random variable x and calculate its expectation. So what I mean by this, so maybe we find out the distribution of random variable x, that with what probability x takes the value 0, with what probability x takes the value 1, with what probability x takes the value 2, and so on. And then find out the expectation using the formula that, like we know how to find the expectation if we are given distribution, right? Like 0 times probability that x is equal to 0, plus 1 times probability x is equal to 1, plus 2 times x is equal to 2, and so on. And so if we try this approach, then this is a bit more complicated approach, but let's just try. So, so let's say that we try to find out this formula, that this value, that probability x is equal to some value I. So note that x, so the probability that x takes the value I, like where I, so note that is I can just take values from 0 to capital R, because there are R distinct red balls. So the number of red balls that appear before all the blue balls can be at least 0 and at most R, because there are at most R red balls. So this probability is 0 if x is less than 0 or x is greater than R, right? If I is less than 0 or I is greater than R. If 0 is less than equal to, if I is between these values, then what's the probability that x is equal to I? So what we need to find out here is that there are I red balls before the first blue ball, right? And how many ways can this happen? Uh, in how many ways can this happen? So there are, note that there are R distinct red balls, right? So from these R distinct red balls, just remember like combinatorics, which we have learned in high school also. So from R red balls, I need to choose I red balls to place before the blue balls appear, right? So what we essentially are going to say is that, one second. So, yeah. So what we are going to say is that we take R red balls and the R distinct red balls. From the R distinct red balls, I choose some eyeballs. So first I'll choose some eyeballs from these R distinct balls, and that can be done in RC I ways. So from these R balls, I choose some eyeballs, I red balls, and I place them at the front. So if I have placed all these red balls at the front, uh, then what this means is that, yeah. And now what I'm going to do is, and now from these eyeballs, since all of these eyeballs are actually distinct, these I red balls are distinct. So if I place these eyeballs at the front, I can also permute them in I factorial ways. Maybe I should do this in form of an equation rather than this. Then it will be much easier to follow. So insert. mm, yeah, equation. Okay. Yeah. Yeah. So what we can do is So from these R balls, I choose these I balls, and then I permute these I balls in I factorial ways. So note that total number of ways in which these balls can appear is R plus B factorial, right? Because there are like R plus B factorial total permutations. Because there are R plus B balls, all balls are distinct. So they can be permuted in this R plus B factorial ways. And out of these ways, what I can do is I can choose these I can place these I red balls at the front in this much number of ways. But our job is not done yet. What we need is that there are exactly I balls in front. So the I plus 1h ball from the front should actually be uh, a blue ball, if this makes sense. So what we are going to do is so so after this, I need to actually subtract out the cases in which the I plus 1s ball is actually not the blue ball but rather a red ball. And how many ways can that be done? So that will be done in this much number of ways. Uh, so R choose I plus 1 factorial. And why is this the case? So this R choose I times I factorial gives me the ways in which I can place the red balls in the front. And then I just permute the remaining balls. There are like R plus B minus I remaining balls in any manner. So that's why this just becomes R plus B minus I factorial. But now in these cases, that case is also covered where the I plus 1th ball may also be a red ball. So I need to subtract out those cases. So for that, what I do is I say that the I plus 1th ball is also a red ball. And then I do this, and then I just subtract out these cases. I know that if I plus 1th ball is also a red ball, then there are again R plus B minus I minus 1 uh, uh, balls remaining. And these balls can be permuted in these number of ways. Sorry for this. So this is going to be the probability with which x is actually going to be equal to y. And then what's the expectation of x going to look like? So expectation of x is nothing but summation over uh, insert equation. Okay. Uh, I equals to 0. Uh, so I equal to 0 to capital R. So I goes from 0 to capital R, and the summation is about I times probability that x is equal to y. So this is just the standard formula for expectation, right? I times probability x equal to I, and here I goes from 0 to R because probability outside of these domains is just 0. And you can just substitute for this formula, and you will get the answer if you do this kind of a thing. So this kind of approach involves heavy calculations because then you might need to simplify what this sum multiplied by this simplifies to. But do you get the way in which I counted, Swati? Does this make sense? The number of ways in which we counted this solution. So what we did was we just took all the permutation in which I red balls appear before all the blue balls, and yeah, and divided it by the total number of ways. Oh, it makes sense. That's nice. So this is one way to solve, and this is probably very calculative. Involves a lot of calculations, right? Okay, but now let's discuss another approach uh, by which we'll actually be able to give the answer directly, and we won't need all of these things. And it beautifully uses the idea of uh, hmm, it uses the idea of linearity of expectation. Smarter approach. So what we say is, so right now we define this random variable x as the number of red balls that appear before all the blue balls, right? So what we say is, let's just define another random variable xi. Let xi be the random variable, or let xi denote the random variable, which is 1 if ith red ball appears before all the blue balls, else 0. So what we are saying is xi is the random variable. Let us say that xi is a random variable which takes the value 1 if the ith red ball. So there are capital R red balls. If we talk about ith red ball, if the ith red ball appears before all the blue balls, then this random variable takes a value of 1, else it takes the value 0, right? So then actually what we can say is that then it can be seen that, so what's the value of x going to be? So x was essentially the total number of balls, total number of red balls which appear before all the blue balls, right? And what will be the total number of red balls that appear before all the blue balls? This will just be equal to like uh, x1 plus x2 plus x3, and this is the most crucial step. So if there is any doubt in this, please ask Swati. So does this make sense, Swati? Does this step make sense? I think this is the most important step in this approach too. That this capital X can be written as x1 plus x2 plus x3 till xr. So essentially what this is saying is that the total, so this capital X was the total number of red balls that appear before a blue ball. This is just equal to saying whether the sum of essentially whether first red ball appears before all the blue balls, plus second red ball appears before all the blue balls, plus third red ball appears before all the blue balls, till our red ball appear before all the. Okay, so it makes sense. So that's nice. So now what we can say is, and note that what we needed to compute was this thing, like we needed to compute expectation of x, right? And what we can say is that by linearity of expectation, uh, we can claim that expectation of x is equal to expectation of x1 plus expectation of x2 plus dot 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 expectation of x, right? So now we have broken down this complicated term expectation of x into these terms: expectation of x1, expectation of x2, the expectation of x. And what does expectation of xi denote? So expectation of xi denotes essentially the uh, expected value of this random variable, which is 1 if ith red ball appears before all the blue balls, else 0. Right? So then this is another important thing that uh, so note that so suppose we want to answer the find out the value of expectation of xi. So xi is just so x was saying that we have to compute over check over all the red balls, like how many red balls are appearing before the blue balls. But the random variable xi just says that this ith red ball, whether this ith red ball appears before the blue balls or not. So Sadiq, what do you think should be the value of this expectation of xi? So note that there are capital B blue balls And now we have to check whether this ith red ball, this specific ith red ball, appears before all of these capital B blue balls. So what do you think will be the probability, like what will be the expectation of this random variable? So this will be just equal to probability that uh, ith red, okay, sorry, ith red ball appears before all the blue balls. So this is going to be the answer. And what's this probability actually equal to? So would you like to take a guess, Swati? Like any guess is fine. Like whatever you think it should be. Like I just want you to think about it a bit so that this session becomes a very interactive. Okay, maybe Swati is not available. So maybe I'll just answer this on my own. So what's the probability that ith red ball appears before all the blue balls? So note that now we don't need to worry about all the remaining red balls. We just need to think about this ith red ball. So this ith red ball and the capital B blue balls. And we need to say that this ith red ball is appearing before all of these capital B blue balls. And in how many ways can this be done? So note that there are total so uh, so there are so there are these capital B blue balls, and between these capital B blue balls there are B plus one spaces in which the red ball can go, in which this ith red ball can go. And now what we need to say is that this red ball goes into the first empty space, which is before all the blue balls. So out of the total B plus one empty spaces, this ith red ball should go into first place. So the correct, so essentially the favorable number of A's is just one, and the total number of A's is divided by B plus one. So this is the expectation of xi. And this is true for all I. So there are capital R such values. So what we get is like, so expectation of xi is 1 upon b plus 1, and expectation of x is just so this will be 1 upon b plus 1 plus 1 upon b plus 1 r times. So hence we get that expectation of x is equal to, so capital R divided by b plus 1. So this is going to be the final answer. So yeah. So we see that this is smarter and much more compact approach here. We did not need to get into all of these calculations or simplifying the sum. We could just obtain the answer directly by using this linearity of expectation. So like that's why I really like this concept of linearity of expectation. It's a like really nice idea, and it can like help us simplify analysis a lot many times. Okay, then, so if this makes sense, uh, then maybe, so I have a couple of more questions, but I don't think so. So these are a bit more involved, and I don't think so. There are just like 15 minutes remaining, and I don't think I'll be able to answer any of them in 15 minutes. So maybe I'll just discuss the fourth question first. Like, anyways, I wanted you to give this question as a homework for you guys to think about on your own. Uh, But yeah, I just wanted to point out this property to everyone because this is a really nice property. So, so maybe let's just move on to this question fourth first. So, question four says that, okay, so in the lectures, it was shown that determinant of the polynomial by adjacency matrix of a bipartite graph is non-zero if and only if there exists a perfect matching in G. So this is what we have already discussed also that if there exists a perfect matching, then this determinant of this bi-adjacency matrix is non-zero, and otherwise it will be zero. But this only talks about perfect matching. can this statement actually be generalized to maximum matchings? So it turns out actually exists a generalization for this statement. Uh, so suppose that even if no perfect matching exists in G, uh, what we can say is that the rank. So we can still define. So this biadjacency matrix M can always be defined, right? Whatever the bipartite graph given to us, we can always define this biadjacency matrix. And now actually, what we can say is that the rank of this matrix M. So what's the rank of a matrix? Like I hope everyone remembers from like linear algebra course. Like what do we mean by rank of a matrix? And now this is a polynomial matrix. So the rank of this polynomial matrix will be equal to actually the size of the maximum matching in G. So rank is rank on a high level is just the maximum number of independent columns in the matrix set. And note that rank of a n by n matrix is actually equal to n if and only if determinant is non-zero. So actually like this statement this statement that determinant is non-zero means that rank of a matrix M is n. And if we say that rank is actually equal to the maximum matching, then we are saying that the size of the maximum matching is n. And if the maximum matching size is n, then that matching is actually a perfect matching. So actually this statement is a generalization of this claim. And yeah, I would like to you guys to think about this claim, like why is this true? This is a really nice property that the rank of the matrix is actually equal to the size of the maximum matching engine. And yeah, so this is more of a do it yourself kind of an exercise. And there's a small hint for this, which I'll give, like not a small hint, but rather the way by which you will almost be able to get the whole solution, in my opinion. So hint is so for an n cross n matrix, uh, the rank, so for an n cross n matrix M, the rank of M is equal to the uh, is equal to the is so rank of a matrix M is equal to R if and only if there exists uh, an R cross R submatrix of, okay, maybe some matrix, or yeah. So if and only if there exists an R cross R submatrix of M whose determinant is not zero. So yeah. So uh, so this claim that so actually like this problem can be solved by this hint. So this hint is actually a really powerful hint, and this is like used a lot in these randomized algorithms kind of thing. Uh, that rank of a matrix M will be actually equal to R. Like if we say that rank is equal to R, this will be true if and only if there exists an R cross R submatrix of this matrix M, whose determinant is non-zero. Because what do we mean by rank? Uh, by rank of a matrix, we mean the size of the largest set of independent columns, like the maximum number of independent columns of the matrix M. And we know that, so let's say there are R independent columns of matrix M, and then we know that row rank of a matrix is actually equal to column rank of the matrix. So if there are R linearly independent columns, then for these columns there exists R linearly independent rows also. So what essentially we can say is that there are R linear, so there is an R cross R submatrix of the initial matrix M, whose determinant is actually non-zero. And as soon as you uh, as soon as you say that rank is actually equal to this, so as soon as you substitute that value with this, then actually you can show that the expression for this, the determinant of this R cross R matrix, will be similar to what we discussed for this perfect matching, the argument for this perfect matching. And then you'll actually be able to say that if there is an R plus R submatrix whose determinant is non-zero, then there exists a matching of size R. And that's how you say that rank is actually equal to size of maximum matching. So yeah, so uh, a bit to think about, but I don't think it's very, very complicated. Uh, but yeah, this can be done. So yeah. And yeah, so for today, I think this should be enough. So I had another question, which I thought if I have the time, I'll discuss. Like this is kind of, I think, the hardest question, or maybe the hardest, but it was somewhat related to the lectures. So there's the third question. Maybe I'll also give this also as a homework exercise. And a hint for this would be uh, use the same ideas as done in analysis of randomized quicksort. So maybe I'll just describe the problem first. So first we were talking about previously we were talking about quicksort. Like we have discussed in the lectures, like uh, what's the algorithm for quicksort and how do we analyze quicksort. Uh, Now there is another algorithm which is called quick select. Like so, what this says is that suppose you instead of finding the sorted array, you just want to find out the median of the array. You just want to find out what's the median of the given array. So one way is of course to sort the whole array in n log n time and then report the median value. But that's inefficient. Why are you sorting the whole array when you just need to find out the median? So there's this algorithm quick select. What it says is that again, like similar to quicksort, we pick a pivot element uniformly at random. And then what we do is we scan the array and we move smaller elements left of pivot and larger to the right. And pivot is placed at its sorted spot. And now what we do is if the pivot is actually turns out to be at the median position, then we report the pivot as the median. But suppose the actual median is supposed to be to the left of pivot, then we recurse similar kind of a procedure on the left subarray. Else we recurse on the right subarray. So in quicksort, actually, what we did was we had to sort the left subarray as well as the right subarray. But in this quick select, we just move either to the left subarray or to the right subarray. We don't compute on both of these subarrays because we need to see whether median lies on the left side or on the right side, and we move to that part. And now we have to show that the expected runtime complexity of this quick select is order n, or maybe expected number of comparisons of quick select is order n. And yeah, and here also like what I wanted to point out was yeah. So maybe we won't get time to discuss this, but here it will be a bit more tricky than what we did for quicksort. Because now what we'll have to do is again we'll have to say for any pair of elements I and j, we'll define a random variable xij, and xij will be 1 if I and j are compared at any point during the execution of this randomized quick select, and otherwise it will be 0. But what's going to happen is there will be more casework involved. So now this INJ will like there will be some cases when this INJ will never be compared, and there will be some cases when this INJ will be compared at some point. And then now the analysis will get a bit trickier, but not too trickier than quicksort. But you can actually show that here what's going to happen is the total number of comparisons will actually come out to be just order n. Whereas for quicksort, the analysis shows the number of comparisons to be n log n. So yeah. So there is a bit of a difference in analysis. That's why you are losing the log n factor here. But this is a very good exercise to increase your understanding about these kinds of analysis. So yeah. So maybe you can try these questions yourself and uh, this is for Swati as well as Swati who's watching on YouTube. And if there are like doubts in these questions, maybe we can take these up in the next session if we get the time. or otherwise, like, yeah, you can ask this on the forum also. So, okay then, so this was all I had to say from my side. So essentially, like, most of our time was spent on like discussing about the existing concepts because there were a lot of concepts discussed this week, and then we also discussed about some problem statements related to these concepts. So essentially, we talked about how to use random variables, how to understand the ideas of randomization, and we also have a couple of really interesting uh, homework problems also. So yeah, so this is it what all I had to discuss for today. So we still have maybe a couple of minutes left. So Swati, if there are any doubts, any comments, or anything from your side, maybe we can discuss that. If there are no doubts or anything, then maybe uh, we can wrap up the session. Okay, so I don't see Swati typing anything, so I assume that there are no doubts. So I guess then this is it for today. So hopefully I'll see more people in person in the next session. Same timings we'll have these sessions on Tuesdays, 6 to 8 p.m. Same timings every week. So hopefully I'll see you guys in the next session also. And thanks a lot for watching this session, guys. So uh, goodbye and see you next time.